Okay, guys, welcome back. It feels like a long time since I've done one of these, so I do apologise in advance for any mistakes that I might make. Today we're carrying on with complex loci. We're going to do a little bit of a recap at the start because I know it's been a while since we looked at the last one. So do follow carefully, and if you are struggling with this, you really need to look back through the notes and the videos and make sure you catch up. Okay, right, we're going to go straight in. So complex loci, we've done a circle and we've done a the perpendicular bisector between 2 points, and we'll do a bit of a recap on that. So we looked at the equation of a circle basically in the complex plane is written like this. So z minus z1 equals r. Okay. That gives us the centre of the circle, and that gives us the radius. Okay, so you might be asked to do something like this. You might be asked to sketch z minus 5 minus 3i. The mod of all that is 3. Okay, and then find the Cartesian. Now to do that, you need to write it in the, again, you might want to pause the video, but you need to write it in the top form. So you certainly need to rewrite it as 5 plus 3i equals 3. So you've got it in the form, the correct form. And then you know that the centre is going to be 5, 3. We look at it in a coordinate system, and the radius would be equal to 3. So if we're looking on an Argand diagram, real, imaginary, 5, 3 is going to be there, and this circle be like that with a radius of 3. Okay, and you can probably get the Cartesian there. Going to be y minus 3 squared plus x minus 5 squared equals 3 squared if we wanted to write it in the Cartesian form. Okay, so that's the circle. That's a bit of a recap on the circle. The other one we did was the perpendicular bisector, and this was the bisector. We did this before you went into your exams, and it's written in this form, a bisector one. Mod of z minus equals z I, and again you might want to look back at the video, but basically what this means is this is the bisector between the first set is between 3, 0, because that's in the real plane, and the point 0 minus 1. Okay, so in reality what this would look like, 0, 3, sorry, 3, 0, not 3. 3, 0 is there, and the other point 0 minus 1, and it is what this line represents is the perpendicular line. I haven't done that well, but it passes through the midpoint and it bisects those 2 points. Okay, and there are ways you can work out the equation of that line using line geometry. Okay, right, now the third type, which we're doing today, is what we call a half line. Okay, so the equation of a half line. Now a half line is quite simply it's just a line that goes from a point and it goes on forever, but it starts from a point is key there. Okay, so if I look in the complex on an Argand diagram, okay, real, imaginary, and I say I want the half line, I want to describe what the equation of that line would look like in complex vector form. Okay, and it's starting from this point here. Now I'm going to say that point there is, I'm just going to call that vector z1. So z1 takes me to the starting point. Okay, and I'm just going to call this vector z. That point there is variable. That can be moved anywhere on the line. And I'm just going to draw that. So that vector there, I want the equation of the vector z, because z can be moved anywhere on that line. Okay, and I'm also going to add in, I'm just going to put this in just to help us, the argument of that line would be this angle here, okay? Theta. Finally, I'm just going to label that point A, and I'm going to label that arbitrary point B. Remember, that B is on a sliding scale. That could be that point B. I could put anywhere on the line. So let's just imagine that's the. I want the equation of A to B, where B is any point on that line. So the vector A to B. Well, how do I get from point A to point B? Point A to point B. Well, I must go minus Z1. I must go negative down Z1. And I'm going to call this vector Z, because that's the vector that's variable here. So Z1, and then I'm going to add on Z. Now, if I rearrange that, we usually write it in the other order. So Z plus Z1. So that is the equation of that. That's just that is just that vector from A to B. Z plus Z1. Sorry, Z minus Z1. Z minus Z1. So that's that vector. Now I want that vector to be on a specific angle at all times. Okay. At the moment, that's just a vector from this point, or that's just a vector from this point to any point on the Argand diagram. But I want that to go on a specific angle, and I want to make sure that that vector. I want the argument of the vector A to B to be equal to theta. I want that argument to be that angle. The argument of that vector to be the angle. Or in other words, I want the argument of Z minus Z1 to be equal to theta. Okay, and that there is the general form for a half line. So this is this. I suppose this is the angle of slope you can consider, and Z1 is your starting point, starting coordinate. Okay. Right, let's look at an example, and this will tie it all together, and then you can do some questions on this. So it's in the book I'm going to use, but I'm going to try and explain it as I go. So it says, given that arg z plus 3 plus 2I is equal to 3 pi over 4. We've got lots of things we're going to do now. We're going to sketch the locus. Sketch the locus of z. Okay, sketch the locus of all those points that z could be on. And we'll do that first before we tell what the next one is. So sketch the locus of all the points that could be on. So we look back at our general form. And okay, we say we've got to rewrite this first to get z, like we did with the circle. It's got to be minus, and it's going to be 3 minus 2I. I'm just going to rewrite it so it's in the form of the general form at the top there. Right, I know now from what I just proved earlier that the starting point is going to be 3 negative 2. Okay. Again, I've made a slight error there, haven't I? That needs to be a minus 3 because it would be plus 3. So the starting point is minus 3 minus 2, and it goes at an angle of 3 pi over 4. Okay. So from that point onwards, I can draw this now quite easily on the Argand diagram. It starts at the real imaginary. It starts at minus 3 minus 2. Okay, and that's where it starts, and it goes at an angle. Remember, the argument starts in that direction clockwise. 3 over 2 pi is about that angle there, and it just goes on forever in that angle at 3 pi over 4, and that is what z is. Z is anywhere on that line there. Okay, so that is where the sketch would be. Right? Now it says find the Cartesian equation, part B. So find the Cartesian. So what's the equation of that line? Equation of that line. Find the Cartesian equation of the line. Okay. Now this is where we need to use clever right-angled triangles here. So again, any point on the line, any point on line, we can give the coordinates, sorry, not y, we can give the coordinates x, y. And that's the same for any equation of a straight line, or any line. So we know that that coordinate is x, y, okay? Now, I can draw a right-angled triangle here, and I know the height of that triangle. Height of that triangle is going to be y minus the y coordinate there, so minus 2. And the x, the width of that, that right-angled triangle is going to be x minus 3, okay? I also know this angle because it's a straight line. That angle has got to be pi over 4 because they add up to pi. So straight away I can set up an equation here because I know that, remember, tan of the angle, so tan pi over 4 must equal the opposite, which is going to be y minus over the adjacent. Okay, and this in itself will get the Cartesian equation very quickly. So if I do pi get this up. So if I do tan, I need to be in radians of tran, tan pi 4, I get 1, which is quite nice. So I get 1 equals y plus 2 over x plus 3. If I rearrange that question slightly, I just get y plus 2, x plus 3. So y is going to be x minus 5. Okay. Is that right? Yeah. No, not x minus 5. X plus 1 plus 1. Okay, now I've got to be careful here because the gradient is actually sloping. So I've got to be a little bit careful here because, let me just see what I've done. Okay. So the rise is y minus 2 and the x minus 3, so x plus 3. Rise over tan, definitely that, and we should end up this needs to be negative because it's sloping in a way. Check. Tan pi over 4 equals rise. Oh, I think I've made the mistake there. This is not x. To get to this x to there is going to be x minus 2 there, so or minus 3. So that should be a plus 3 there. I made a slight mistake there. This needs to be minus 3. So I did make a slight mistake. I said I would. I knew I was wrong. So I know it took ages there, but I knew I was wrong because y equals x plus 1. That's clearly not the equation of that line. So I know I've made a mistake. So that's good exam technique. Just to go and have a look back at your sketch and just double check that you're writing. So this is definitely y and that's definitely 2. So you're definitely doing y plus 2. This is x and that is 3. So it's actually x minus 3. So just be careful that you do that. So it's going to be x minus 3 equals y plus 2. So we end up with an equation y equals negative x and negative 5, which looks much more likely. Yeah, that's definitely right now. Okay. Now that's the equation of the whole line, but we've got to be a little bit careful because it started at here, and it started when x was minus 3. So I've got to put in the condition y is minus x, but x has got to be bigger than or equal to negative 3 because sorry, I've kind of made a mistake. It will be less than 3. It's going in this direction. It's less than minus 3, so x is going to be less than minus 3. I suppose it could be less than or equal to. In the book they've just put less than. You'd get the marks both ways there. So that's the equation to the Cartesian equation. Right, finally it says find the complex number that satisfies the equation z plus 3 plus 2i equals 10 and what we've just done, arg z plus 3 plus 2i equals 3 pi over 4. So we're trying to find the coordinate that satisfies both of those. Okay. Now, if we look at the left-hand side one, you should notice that that is a circle, and it's going to be z minus 3 minus 2i equals 10. So that means it's got a centre of minus 3 minus 2, and it's got a radius of not root 10, a radius of 10. Okay, and over on this side, this is a half line. We've just drawn it, but it's a half line of starting point is minus 3 minus 2, and it goes at that angle there. So if we draw both on an Argand diagram, what's happening is centre minus 3 minus 2. Okay, which is quite interesting. They both have a centre there, minus 3 minus 2, and the radius, the equation of the circle, I'm not going to draw all of it, but it's going to go all the way around like that, isn't it? And the equation of the half line is one that goes up like this. What they want is they want you to find the coordinates of that point, or that's the vector. So we'll see, that's what we're trying to work out. We're trying to work out where that point is. Now the way I'd recommend doing this is by looking at the Cartesian equations. So if we look at the circle, we know the circle is going to be x minus, so x plus 3 squared plus y plus 2 squared equals 10 squared. And the half line, we did just work that one out, I think. That was the same one we just used. So look back up the video and it's y equals minus x minus 5, and you can solve that equation and you'll get two solutions, and you just need to make sure you pick the right solution there, and you'll find that the right solution should be x is minus 3. I'll let you solve that. It's a quadratic simultaneous equation, and y should equal minus 2 plus 5 root 2. So in complex form, we would say z is equal to minus 3 minus 5 root 2 plus I, and then minus 2 plus 5 root 2i. Okay, and there you go. So that is the lesson. There is an alternative method to that in the book on page 33 that you might want to look, but I think the Cartesian way is a bit more simple to get your head around. So try and look at that and work through it. I appreciate you haven't really covered, you haven't seen this for a while, so I do want you to do a fair bit of practice on this. Now it depends on where you left off. I want you to do question, let's go for question, actually page 35 please, question 11 all the way up to 19. Okay, and I do expect you to complete nearly all of that before the next lesson. Okay, so it's 11 to 19, and you might want to have a go at the challenge, and then next lesson we'll be moving on to regions. Okay, so that's it for today, guys. Just go through it slowly. It is a tricky topic this, but just work through it slowly and you'll be fine. Okay, speak to you again soon.